Commercial myoelectric prostheses lack the ability to provide proprioception to their users. As a result, when a person with an upper limb amputation moves his prosthesis, he doesn't know where it is without having to look at it. In this project, we present a passive linear skin stretch device that can provide proprioceptive feedback when controlling multiple degrees of freedom in a prosthetic hand. We modified an open-source 3D printed robot hand developed by InMove with custom pulleys that pull tendons moving both the fingers and contact pads adhered to the forearm. The pulleys and contact pads cost less than $2 in raw materials. When a finger moves, a contact pad is displaced by a proportional amount, and the subject correlates the amount of perceived skin stretch to the angle of the finger. Our first experiment involved controlling the angle of a virtual finger to match a target angle while giving no positional feedback, feedback using our skin stretch device, or feedback using a vibrotactile array. For the vibrotactile array, a specific motor vibrated when the finger angle entered a particular range. Here we see a subject using the skin stretch feedback device. EMG is used to control the position of the finger, and the white contact pad provides skin stretch accordingly. The subject's fingers are fixed so that he can only rely on the feeling of skin stretch to determine the angle of the finger. In training, his goal is to follow a target virtual finger, shown in red, by controlling the virtual finger shown in blue. During evaluation, the prosthesis and blue virtual finger are hidden from him, and he must match the red target angle based off of skin stretch feedback alone. Our results show that there was no statistical difference in performance between the skin stretch device and vibrotactile array, and both performed significantly better than when no feedback was given. In addition, our skin stretch device takes up less surface area and drains less power than the vibrotactile array, and subjects reported that it was less distracting than having vibration always on. Extending our device to multiple degrees of freedom, we attached 2 additional contact pads to the radial and ulnar sides of the forearm, corresponding to the thumb and middle finger joint angles, respectively. Subjects were asked to distinguish between 6 grips, all beginning from an open hand configuration. Here, you can see how multiple contact pads are displaced for particular grips. After a brief 6-minute training session, the prosthesis is hidden to the user, and the 6 grips were presented to him 5 times each in random order. On average, subjects were able to correctly classify the grips with 88% accuracy. In our final experiment, we asked subjects to match a particular grip aperture using EMG. Subjects were presented with either skin stretch feedback or no feedback at all. Here you can see the subject controlling the aperture of a pre-selected grip to various percentages of closure. For 30 different combinations of the 6 grips and target apertures, the subjects matched the grip apertures with 11.1% error on average. The simplicity, low cost, low power consumption, lightweight, small contact area, and overall comfort make our passive linear skin stretch device well suited for multiple degree of freedom proprioceptive tasks. In the future, we hope to extend this feedback to even more degrees of freedom and implement it on commercially available myoelectric prostheses.